Okay, so the last bit of material that will be on the final exam is a little bit on design for in-service properties of nickel superalloys, primarily creep and fatigue life. Creep is the primary design constraint, and just for those of you who haven't taken Professor Mill's high temperature deformation class, we'll just consider creep as the time dependent deformation of a material under constant load or constant stress, primarily at elevated temperature, right? And so the stresses for creep are usually going to be much lower than the yield stress, right? It's going to have a exponential dependence on the stress. So small increases in stress can have a very large change on the creep life. And because normally this happens at high temperatures, it's thermally activated. So it has a Arrhenius dependence with temperature, and the environment can also affect creep rates. Oxidation in particular can play an important role in the acceleration of creep. So if we look at a creep curve, this is highly schematic, but we have a primary creep region where the strain rate starts high but decreases, and then this regime of approximately steady state creep where the strain rate is approximately constant, and this is sometimes the slope here is often referred to as the minimum creep rate, and then this region of tertiary creep where damage, thank you, no problem, where which marks the onset of damage and the beginning of the rupture process, right? So if we keep temperature as a constant and we increase the stress, right, we're going to move the curve in this direction. And often for superalloys, you don't have a clear, this region of secondary creep is quite small. So you have an extended primary creep region, right, which then it never really saturates out to this kind of minimum long linear region before damage happens. So this primary creep curve just gets extended way out sometimes. But most of the microstructural changes in the material are happening in this primary creep region. So this is the region where the microstructural evolution that we talked about last time, the dissolution of gamma prime, the change in gamma prime morphology, all of this is largely happening in this primary region. And when we think about secondary creep, this essentially means that we're in a regime where the microstructure is fairly constant, right? Think about a stress strain response, and how would it stay at a constant deformation rate if the microstructure itself was not in approximately a steady state, right? And we have to think about in metals at least, we have 4 primary mechanisms, right? We have dislocation glide, that's thermally assisted, right? So, all right, dislocation climb, again, thermally activated dislocation climb, grain boundary sliding, and then diffusional creep. And we can largely ignore diffusional creep because this is at very, very high temperatures relative to melting. We don't want our material that high. So largely for superalloys, we're going to think about dislocation glide, climb bypass processes, and then the motion of grain boundaries, right? So each mechanism, of course, has a different optimum microstructure, right? The important thing to note is that creep and fatigue are our two design constraints, typically, and they have exactly opposite requirements on the microstructure, right? For creep, we want large grains. For fatigue, we want small grains, right? So there's always going to be a balance, right? We're not going to get into exactly where this expression comes from, but this is a kind of a common engineering approach, is to write the steady state creep rate as a power law prefactor with an exponential like this. Q, this is the activation energy for creep. So for a solid solution alloy single phase, this is just going to be the same activation energy for self-diffusion. But when you have secondary phase particles, this activation energy for creep is much higher than that for diffusion. The stress dependence has a power law here, right? The notes, these notes, again, this is a slide from Jim Williams' course that he gives. This N value here is the stress exponent, right? And this is going to be strongly mechanism dependent, right? So the classical values that if you just look in the regular metal literature, this is going to say N values of 3 to 7 for solid solution strengthening. For superalloys, this stress exponent can be as high as 20 for different different mechanisms at work, right? And this all has to do with the activation energy and the activation volume of the different processes. If you're really keen on understanding the sort of the physical origin of this strainer exponent, I just published a paper last year where we did a model where we put a backstress in here and showed that we can, with the appropriate backstress from dislocation interactions with the gamma prime, we can reduce the stress exponent down to the mechanisms that are predicted for solid solution strengthening. So this high exponent for superalloys is really a function of the dislocations interacting with the gamma prime particles, right? But I don't want to get too much more into the details on it than this. This is kind of a slightly outdated picture. This is from a famous image that Professor Mills put together that sort of shows the stress versus temperature dependence of all the different creep mechanisms that are common in high gamma prime fraction superalloys, so primarily blade alloys, but at low temperatures and high stresses, it's this APB coupled shearing where you've got two essentially full dislocations moving through, leaving a anti-phase boundary between them. As you go up in temperature, other mechanisms become thermally activated. So you start to do dislocation looping, isolated faults, meaning individual gamma partials start to move through, leaving complex stacking faults behind. Then micro-twinning, dislocation climb bypass, and then is the highest, but this micro-twinning and extended faults these are dislocation cutting mechanisms that require a local rearrangement of the atomic structure, right? So it's not just a shear, it's a shear and a shuffle of atoms diffusing from one plane to the next to accommodate these. So the mechanisms at play become very complicated very quickly. And this is just kind of a schematic picture. We're not going to talk about the details of any of these, right? And then once you start to get up here, you start to dissolve significant amounts of gamma prime, your stress levels drop even more because now it's behaving just as a regular solid, single-phase solid solution, strengthened alloy. So the big danger, the ultimate failure with creep is the rupture process. So actually of interest, if you think about a disk, it's not going to have to creep all the way to failure for really bad things to happen, right? Think about the inside of a turbine, right? You've got all these disks rotating, right? And the disks are moving between vanes, right? You have this, and you want to minimize the amount of losses due to aerodynamic forces, right? So that means the tolerances in there are really close. And in fact, a lot of engines actually have something, Pratt & Whitney calls it turbo tip, which is essentially sand glued to the top of the turbine disk so that when it starts up, there's clearance. And as the blades expand from thermal expansion, they actually cut clearance into the casing, right? And so they'll wear their own perfect fit path. And then after several hundred rotations, that sand is abraded away and just goes out. So the amount of strain that can be accommodated in these disks before they start doing things like rubbing, right, is bad, right? You don't want things hitting other parts of the engine while they're spinning. But the ultimate failure mode is going to be the stress rupture process from cracks that are originating at the grain boundary. We can think about a disc alloy where we have a polycrystal, right? So our initial condition is this gamma prime intergranular. As we start to creep, we're going to agglomerate. Our gamma prime is going to become agglomerated at the grain boundaries. We're going to form the MSE type carbides, which are then going to age in and form these M23C6 type carbides that are going to agglomerate. As this happens, as these carbides are formed, our grain boundary region becomes denuded of gamma prime, right? Just like a precipitate-free zone in aluminum. So we have a grain boundary region that is now softer because we don't have the strengthening phases, and our carbides grow larger, and eventually this leads to micro cracking at these interfaces, right? And this is just a schematic picture of the ultimate kind of failure mode, right? And so here, just observation, this is a large M23C6 carbide that's coarsened quite a bit, and here we see a region that's pure gamma that's been denuded of gamma prime particles. A lower mag here where we see a crack forming at the interface of these large carbides, right? So that's the sort of the design criteria for creep. Fatigue, of course, we're thinking about cyclic loading, right? And this just is one simple path, of course. As you do multiple cycles, the area of this curve will change, and there's going to be some hysteresis in the process, right? And if we think about the life is going to be limited by the number of cycles until crack initiation, and then the crack growth rate, which is the elongation per cycle, right? It's not, it's like one of those things, right? As engineers, there's some things we don't talk about, right? And one of those things is you don't tell other passengers on the airplane that there's lots of micro cracks in the engine. It scares people. You don't mention about cracks in power plants or things like that. But, in every engine, there are cracks. Just happens to be that we're in the regime where the growth rate is still small. What we definitely want to avoid is, right, we have is low cycle fatigue failure, right? So we can quantify that as where the increment in elastic strain is less than the increment in plastic strain, right? And this is just kind of a rough thing. And so we can think about this as the, 1,000 to 10,000 cycles, right? And what's the primary low cycle fatigue event, right? This is the number of engine startups and shutdowns, right? So this is the number of flights that an engine takes. High cycle fatigue is completely in the elastic regime. So the elastic strains are much, much larger than the plastic strains. And when we say completely in the elastic regime, of course that means macroscopically, right? Locally, there can still be stress concentrations, right? Local yield happens well before macroscopic yield, right? So always keep that in mind. But like 10 to the 6 kind of cycles, and this is the vibration that the blades see in service, right? As the rotor's spinning around, right? So this is vibration. This is engine cycles. Our discs and rotors are typically going to be low cycle fatigue limited, right? So what's done is putting a compressive stress on the surface, typically by a shot peening operation, right? So, really common manufacturing step in turbine engine parts is shot peening or ball peening or some other mechanism to put a compressive stress on the surface. This way, there is no opening force for crack. So if you have a flaw at the surface, right, it has to overcome the compressive stress in order to open, right? Airfoils are not limited by low cycle fatigue, right? These are also can be, I'd say almost always are, going to be peened. But they would be high cycle fatigue, but typically they're taken out of service well before that happens, right? They have other failure mechanisms before then. So the life of the blade is high enough that we're worried about creep failure or other types of coating spallation or other types of damage well before the high cycle fatigue limit is reached, right? So if we're thinking about designing discs and doing material selection for discs or designing alloys for discs, we keep pushing operating temperatures higher and higher. Well, okay, so blades we'll talk about, but blades are actively cooled and they have coatings on them, right? And they're single crystal. right? The discs have to be polycrystal, random textured. There's no good active cooling mechanism for them, right? They're just this big rotating hunk of metal, right? So going to higher temperatures means the design criteria is shifting away from fatigue towards creep, right? Historically, these were done by cast and wrought, right? So you would make a casting of an approximate shape of the disc and then put it into a forge press and forge it to the final shape. Nowadays, the big discs are all made by a powder metallurgy route, right? Which adds a lot of cost, but we'll see has a lot of benefits, right? So we're really the primary driver for the development of disc alloys is for creep design, right? So there's a whole bunch of fun stuff going on. People are doing what they call hybrid discs, right? Where they're trying to make discs that have small grain sizes near the hub, where fatigue issues are still a problem, and coarse grain near the blade roots, right? Where creep life is an issue. Of course, now you have location-specific, microstructure location-specific properties. That adds a whole bunch of processing issues, right? And a whole bunch of new inspection capabilities, both in-service inspection and during manufacturing. Particularly high-resolution ultrasonic. People are doing all kinds of stuff with backscattered ultrasonic now, where they can measure the grain size by looking at the backscattered signal, which is normally just considered noise. But these are things that need to be considered, right? So basically, as we go, this is up in time, increasing temperature capability, right? And some basic trends with time. IN 100 and Rene 88. These are both, I'd say, more or less modern alloys. There's still things we look at quite a lot, but these are both powder metallurgy alloys, right? And if we look at the creep time from forging to PM route, right? We've actually have improved the creep life of superalloys by 2 orders of magnitude, right? With new compositions over the last 20 years, right? I can't think of a lot of metallurgical properties that we've been able to improve by 2 orders of magnitude, right? That's huge, right? That'd be the same as going from a 20 megapascal yield strength to a 2 gigapascal yield strength, right? It's crazy. So the development of powder metallurgy processing for superalloys had a lot to do with that. All right, so basically the route is you have a melt. It's poured into a gas atomization, right? And then you have to pull out all the oxide removals, right? So there's a very expensive sieving process, right? And this has very low yields, right? This is not an efficient way to produce material, right? Then it's poured into a can with vacuum. This is essentially a can in the shape of the part, right? So it's tooling that's in the shape of the part that you're doing. This is pulled under vacuum to degas, and then typically laser welded. The can is sealed, goes into a hot isostatic press where the material is sintered, right? You can think of sintering is the opposite of creep, right? The opposite of diffusion creep, right? We're consolidating particles rather than in creep moving the center of particles apart. Same physical mechanism, just going in opposite directions, right? This extrusion process is not really used much anymore for production. It is used a lot for fabricating samples, right? But we go through all that. We have there's a lot of places where inclusions can get in, either impurities in the feedstock that we're melting, right? We have a vacuum induction furnace. We can have bits of liner from this induction furnace, right? You can have reactions that happen during the atomization process, impurities that are entered during powder handling and transport, or in the containerization process, right? So these things happen, right? Here's an inclusion of some kind. I don't know what it is, but nothing bad happened, right? No apparent cracks, right? So here we've got an inclusion where the inclusion is cracked. So this is some kind of brittle foreign particle, and that is beginning to extend into the matrix. Right here, we've got an inclusion that's cracked that ends completely at the matrix. Here we have an interesting case where the crack comes and then wraps around the particle and continues on. So crack follows along the interface between the inclusion and the matrix, right? And the melting crucibles were a major source of contamination in powder PM alloys. So these are particles, cermet particles from the crucible that led to low cycle fatigue, crack initiation, and in-service parts, right? So these were parts that failed in an engine, right? This wasn't found on inspection, right? So I mentioned peening before, right? So these low cycle fatigue cracks will either initiate at an easy inclusion. If there are no inclusions, that's great, because that means they'll initiate at the surface, right? And this is the log cycles to failure, right? Again, highly schematic, but you can see simply peening really increases the resistance to crack opening, right? For a given stress to cause a failure, you have to go up, for a given number of failures between peened and not peened, you have to go up a large amount of stress, right? Or the other way, if they can get, for the same stress, the number of cycles to failure goes up quite dramatically by peening, just from putting that surface compression on it. And now we're looking at all kinds of different cool techniques, like laser peening rather than shot peening, right? Getting highly localized compressive stresses, right? Okay, so that's thinking about discs. For airfoils, we have high pressure turbine and low pressure turbine. The high pressure turbine is, of course, the hottest part. So these are cooled blade, and they're going to have a thermal barrier coating on them. Low pressure turbines are solid and an environmental coating. The shrouded tip, right, is just essentially what it means. It's another airfoil that's on the top that help control. The history of these, so this is pre-drilling because you notice it doesn't have any cooling channels, but this is a high pressure turbine. Original designs were essentially cast and wrought blades, so they had an equiax grain structure. Then they moved to directionally solidified blades, and now almost everything is single crystal. All right? So what, I mean, you guys have it in front of you, but what do you think is the big issue, the biggest challenge with single crystal? All right? You're growing this crystal when you cool it, right? Is this a single, this isn't pure nickel. You got a whole bunch of stuff going on, right? You got a whole bunch of alloys, right? So as cast, these are highly dendritic microstructures, right? We haven't talked about dendrites really in this class, right? Because normally we're not considering things in the purely solidified state. Usually we're doing a whole bunch of extra stuff to it to put metal in service, right? But the general rule of thumb is going to be the thicker the casting, the larger the primary dendritic arm spacing. That's what PDAS stands for. Right. Coarser particles, larger fraction of eutectic material regions, and greater solute segregation in between the dendrite arms, right? As we go to thinner castings, we solve these problems, but our fatigue life gets worse, right? So, and because, remember, a lot of our alloying elements are heavy refractory, right? The tungsten doesn't move very quickly. Niobium doesn't move very quickly, right? So this inhomogeneity persists even after solutionizing heat treatment, right? So we can dissolve, take it up to high temperatures, right? And we still don't equalize composition, even if we dissolve the gamma prime, right? So just a refresher, I know you had this in phase transformations and that, but if we remember, if we have alloy composition at composition B, right, our first material to solidify is going to be of composition A, right? And as we move down, the composition of our solid gets greater, but also our liquid concentrates in solute as well, right? And so now we have this is what leads to our dendrite coring, right? We have a compositional gradient throughout the dendrite, but we also have a gradient in our liquid concentration, right? And our max solute in the liquid, and right before the last liquid to freeze, will be much, much higher in solute than the first solid that froze, right? And remember that our solute is going to segregate during solidification, right? So we've got this concentration gradient out front, right? And as we solidify, this is the, right, this picture is the schematic of zone refining, right? Right? How high purity silicon was made, right? The patent on zone refining, pushing the solute out by selectively, right, taking a moving heat source and moving it along and selectively partitioning solute atoms to the liquid phase repeatedly, right? The patent on that paid for the operational cost of Bell Labs in its entirety for the whole time that patent was available. The only other time I could think of something like that was for the Fraunhofer Institute. What did they have a patent for that essentially netted them a huge amount of money? They had the patent for the MP3, right? So you can imagine when that patent was alive, right, it essentially paid for the entire operating cost of the Fraunhofer Institute. Didn't cost the German government a penny, right? So where do these dendrites come from, right? Compositional supercooling, right? This is our solid-liquid interface position, right? This is the actual physical temperature gradient of our liquid, but as we put all that solute in there, we're going to depress the freezing point of our liquid. So we have a region here where our actual temperature is below our freezing point, and we have a region of supercooling, undercooling, right? And this is what leads to the instabilities that cause the dendrite arms, right? And so just a little bit of refresher. I know you've seen it several times, but it never hurts to think about this again, because for the grad students, this is a really easy candidacy exam question that people like to ask, right? Because it's one of these common things you've seen a million times, but it's so easy to screw this chart up, right? Right? And then you have Professor Drasia drilling you, right? So it's good to see it again. So if we want to go to higher temperature capability of airfoils, we're running out of our ability to raise the surface temperature of the metal itself, right? There was, people thought cobalt superalloys were going to be an answer to that because the melting temperature of cobalt by itself was so much higher than nickel, and that even though it weighed a lot more, and plus it weighed less, sorry. It costs more, but who cares about cost? It's a jet engine. The problem is the gamma prime solvus in cobalt is so much lower than in nickel. So people haven't been able to take advantage of developing really practical cobalt superalloys yet. But we're really running out of the room we have to increase the temperature range of the superalloys themselves. We can add more refractory elements, right? Tungsten, tantalum, and rhenium. But my God, rhenium's expensive, right? We can remove the chromium to stabilize the gamma prime at higher temperatures, but then we run into hot corrosion problems, right? And higher risk of microstructural instability, primarily through the formation of omega phase. Not omega phase, TCPs, topological close packed phases is what I meant to say, right? So we have to do engineering designs, better cooling structures, but it's really difficult to cast single crystals with all these intricate cooling channels in there, right? And then there's a lot more machining steps after, and better use of thermal barrier coatings, right? But we've done pretty dang good, right? This chart still is almost 20 years old now, but these are still alloys that are in use, right? But you can see the real trend for going from single crystal to directionally solidified to single crystal. I said that wrong. Polycrystal, directionally solidified, single crystal, right? The trend that goes up. Here's what the castings look like, the cooling channel, right? You have two air channels that come in down here, right? That force cooling air in, out through these holes, which then you have a thin film of cool air on the surface, right? You get a thin layer of, the idea is you want laminar flow of cooling air across that blade. But this is just really, really complicated internals. Right? And the other is thermal barrier coatings. And this is what I did when I was at Pratt & Whitney. I can tell you right now, this is applied by electron beam physical vapor deposition, EBPVD. Thermal spray is the other primary way of doing this, but EBPVD gives you these nice columnar grains so that as you don't have issues with thermal expansion mismatch, right? Because these grains can handle a lot more strain in this direction than a solid thermal spray coating can. But here's your turbine disc. There's a bond coat, which is an aluminide layer, which diffuses into the surface of the nickel superalloy, but has a good match in lattice parameter and coefficient of thermal expansion with the zirconium, right? This is yttria stabilized zirconium, YSZ, typically about 7% yttria. All right, what's the yttria there for? Any idea? What does it stabilize? It stabilizes the zirconia, but what does it stabilize in the zirconia? It's a martensitic transformation, right? It goes tetragonal to monoclinic, right? And you want a cubic tetragonal monoclinic. And you want to keep it in the cubic zirconia phase, right? The same phase that are used to make fake diamond rings, right? Or used to be before they have much better fake diamond rings now. Right? Okay. So future generation turbine airfoils, it's really all about cooling and aerodynamic design. We're running out of room to improve the superalloys themselves that much anymore, unless someone makes a major breakthrough in cobalt, which I'm not anticipating. I think cobalt is going to come into play in better disc alloys and polycrystalline case, right? Essentially, to fix the gamma prime solvus, you have to put so much nickel into the cobalt that you've added your weight back and reduced your melting temperature to the point that you might as well just use nickel in the first place. So not so much good for blades, but these things are insanely expensive to produce. You have to grow a single crystal. You have to do a lot of high precision machining, right? Then you have to do all the value added steps of the shot peening, the coatings, right? So alternates, I think my personal feeling is carbon matrix composites, right? These are, oddly enough, these are silicon carbide composites, which sounds weird, but you take fibers of silicon carbide and then do a melt infusion. So you have silicon carbide fibers and a silicon carbide matrix. But you have directional, silicon carbide has about 1,000 crystal structures, right? If you look at the phase diagram of it, it's really complicated. But there's tests going on. GE is doing live engine tests of CMC blades at military temperatures with no cooling, solid blades without any thermal barrier coating, just an environmental coating to prevent erosion and hot corrosion. So I think, honestly, this is probably where we're going to go for blades next. Titanium aluminide. There was a huge amount of work done in this like 10 years ago, and it's gone nowhere. Right? Absolutely nowhere. So I don't expect much to happen there. I'll put that on YouTube, and that will be the thing. They'll give me a nasty comment. Someone will be like, how dare you say? It's always, the comments on YouTube make me depressed because it's never like anything positive. It's always like, Professor Badisha gave a much better lecture on this. It's like, well, yeah, well, he's Harry Badisha. He wrote the book on steel. Go listen to his lectures. But I did find errors in his titanium lectures. So, but I didn't write nasty comments on his YouTube channel. Right? But basically, that's where we're going to stop up. This is just the trends. Right? There's nothing new. Higher refractories hurt oxidation. We want to go to higher temperature. We need cooling air, blah, blah, blah. Right? The big environmental effects are oxidation and hot corrosion, right? And this is the increase of refractories and the reduction of chromium are the two big problems with causing these. Okay, so that's it for material that will be on the exam.